Hi everyone, today a video on the amount of substance topic, looking at relative atomic and molecular masses, the Avogadro constant and the mole. So the actual mass in grams of an atom or a molecule is far too small to actually find by weighing it on a set of scales. So instead the masses of atoms are compared to each other and relative masses are used. Now, many years ago it used to be that this was referenced that an atom of hydrogen had a mass of 1 and every other element was relative to that. Now the actual definition that we use is that the relative atomic mass, which is given the symbol Ar, is the weighted average mass of an atom of an element taking into account its naturally occurring isotopes relative to 1/12 the relative atomic mass of an atom of carbon-12. So what we mean by this is now we're not talking about hydrogen as 1, but we're talking about 1/12 of carbon-12 as 1. Now in practice actually the difference is very small, but the definition that you should learn is that it's 1/12 the relative atomic mass of an atom of carbon-12. The other important thing to note here is that we have the average weighted mass of this element. It takes into account its naturally occurring isotopes, and so the reason why is we have to account for the fact that some elements have multiple naturally occurring isotopes with different percentage abundances, and we'll see that we can calculate these values of atomic mass from mass spectrometry data. But for a really simple example, we know that chlorine exists with an atomic mass of 35.5 if you look at your periodic table, and the reason for that is because actually the naturally occurring isotopes are chlorine 35 and chlorine 37, and it exists as 75% chlorine 35 and 25% chlorine 37. And so the weighted average of 75% of 35 and 25% of 37 gives us 35.5. We can also write it down as a more sort of mathematical equation, and so we can say that Ar is the average mass of one atom of an element divided by 1/12 the mass of an atom of carbon-12. Similarly, we can do a very similar thing for molecules. So we have a relative molecular mass given the symbol Mr, and this is the mass of that molecule compared to 1/12 the relative atomic mass of an atom of carbon-12. Now note we don't have to have that weighted average bit in because the weighted average part of it has been already included in the atomic mass, and so it's simply the mass of the molecule compared to 1/12 the relative atomic mass of an atom of carbon-12. And we find Mr by just adding up the relative atomic masses of all the atoms that are present in the molecule, and by that we need to find the formula of the molecule. So we look for what the formula is, see what atoms are involved and how many there are, and we just simply add up the relative atomic masses that we find on the periodic table. And so again we can write a more mathematical formula where Mr is the average mass of one molecule divided by 1/12 the mass of an atom of carbon-12. Now, there's a slight sort of technical description and difference here between relative molecular mass and something called relative formula mass. And this is because ionic compounds exist as a formula unit. They don't exist as a molecule. They exist as a compound. And so the term relative formula mass is used for ionic compounds, relative molecular mass for covalent compounds. So, time to have a go at some questions. So if you'd like to have a go, pause the video and the answers will be on the next slide, but we have to calculate some relative molecular masses and then say which of those are ionic compounds. So to calculate the Mr, remember what we said, we're just going to sum the atomic masses of all the elements that are involved in our compound. So first of all, ammonia, NH3, so we have nitrogen, the atomic mass is 14, and we have hydrogen, but we have 3 hydrogens, so we need to do 3 times the atomic mass of hydrogen, which is 1, and that gives us our answer of 17. Now if you look on the periodic table, you'll see that your atomic mass is given to 1 decimal place. For example, nitrogen is 14.0, carbon is 12.0, chlorine is 35.5, and because it's given to 1 decimal place, we have to give our Mr values to 1 decimal place as well. So the answer for ammonia is 17.0. B is sodium chloride, NaCl, so we simply have the atomic mass of sodium, 23.0, the atomic mass of chlorine, 35.5, and this gives 58.5 as our Mr. Then we have this ammonium sulfate, salt. So we have, the key thing here is to note that we have NH4 and then in brackets 2. So we actually have 2 lots of nitrogen, so that's 2 times 14. We have 2 times 4, so 8 hydrogens, 8 times 1. Then we have 1 sulfur, which is 32, and 4 oxygens, so 4 times 16, and the sum of all that is 132.0. And then finally, the sodium carbonate with the 10 waters of crystallization. If we have a molecule like this, such as we have with the 10 waters of crystallization, we also have to include that in our MR calculation. The 10 waters are part of that molecule. So we have 2 sodiums, 2 times 23, a carbon, which is just 12. We then have our 3 oxygens from the carbonate, so 16 times 3. We then have 20 hydrogens, because it's H2O, so 10 times the 2 H's gives us 20 of them, so 20 times 1. And then the 10 oxygens that are in water, so 10 times 16. And the total comes out to be 286.0. So the really important thing to take away from this is that we always include all elements that are in our formula, and we always give atomic masses and molecular masses, the values of them, to 1 decimal place. And then secondly, it was to ask which one of these was ionic compounds. And so the ionic compounds here are the sodium chloride, the ammonium sulfate, and the sodium carbonate. They're all composed of ions. And of course, ionic compounds exist as compounds, not as molecules, so we can't use the term relative molecular mass, we have to use the term relative formula mass. So this brings us on to something called the Avogadro constant. Now, to count atoms, because atoms weigh so little, a single atom weighs so little, we have to weigh very, very large numbers of them, because they're impossible to weigh individually. And so if we weigh out the relative atomic mass of any element in grams, so for example 4 grams of helium, which has an atomic weight of 4, 1 gram of hydrogen, could be 12 grams of carbon, it could be 23 grams of sodium, anything like that, where we weigh out the relative atomic mass in grams, this amount will contain the same number of atoms. So 4 grams of helium contains the same number of atoms as 1 gram of hydrogen or as 12 grams of carbon. And if we weigh out the relative molecular or formula mass, the MR of a compound in grams, for example 18 grams of water, then we also have the same number of entities. Now the word entity is a useful word to use here because entity can mean anything. It can mean atoms, it can mean molecules, anything like that. It can mean ions. Now what we actually mean is that 18 grams of water contains the same number of molecules as there are atoms in 1 gram of hydrogen or 4 grams of helium. It's an important distinction to get right. If we're talking about a single atom, a single element, then if we weigh out the atomic mass, all of those amounts will have the same number of atoms. So 4 grams of helium has the same number of atoms as 1 gram of hydrogen. Of course, water exists as a molecule. So if we have 18 grams of water, well, 18 grams of water contains the same number of molecules, not atoms, molecules, as there are atoms in 1 gram of hydrogen or 4 grams of helium. And the actual number of atoms in 1 gram of hydrogen, or it could be 12 grams of carbon, or 4 grams of helium, is 6.022 times 10 to the 23. And this is the Avogadro constant. It's the number of atoms in 12 grams of carbon-12 is the formal definition. But essentially, it could be the number of atoms in 1 gram of hydrogen, 4 grams of helium. We could also define it to be the number of molecules in 18 grams of water, for example. And so then this brings us on to something called the mole. So if we have an amount of a substance that contains 6.022 times 10 to the 23 particles, i.e. it contains Avogadro's number of particles, this is called a mole. So the amount of substance that contains that number of particles, we could say that 1 mole of water is 18 grams of it, because we know that 18 grams of water, which has a molecular mass of 18, contains Avogadro's number 6.022 times 10 to the 23 number of molecules of water. We can also say that 1 gram of hydrogen, 4 grams of helium, 23 grams of sodium contains that Avogadro's number of particles and hence is a mole. So the relative atomic mass of any element in grams contains 1 mole of atoms. and the relative molecular mass or formula mass of a substance in grams contains 1 mole of entities. And there's that word again, entities. It could be molecules, it could be ions, it could be electrons. Just make sure you know what the entity actually means in that case. And so the Avogadro constant is a number of particles in the mole of a substance. And so it's really important to know whether we're dealing with atoms or molecules. So it's really important to give the formula for what you're dealing with. 1 mole of hydrogen could mean we have 1 mole of hydrogen atoms, simply H, or 1 mole of hydrogen molecules, H2. Of course, H2 would contain twice as many atoms as just H. And the reason why we have to use moles is because it allows us to compare the numbers of different particles that take part in chemical reactions. Now, you sometimes might also hear the term molar mass. This is simply the mass per mole. It has units of grams per mole, and it's the same numerical value, it's the same number as what the MR is. But you may just hear people call it the relative molecular mass, you may hear people call it the molar mass. If it's called the molar mass, then it has the units of grams per mole. And so when we start to think about moles in terms of actual numerical equations, we can say that the number of moles, which is given the unit mol, M-O-L, is the mass in grams divided by the molar mass, or the MR. If we're dealing with molar mass, it's in grams per mole. And hopefully you can see that if we do grams divided by grams per mole, the grams cancel out and the per mole goes up to the top, and that gives us our unit of mole for the number of moles. And so we can write this out using symbols. The N, number of moles, is equal to the mass, M, divided by the molar mass, or the relative molecular mass, MR. So, time to have a go at some questions. So there's questions here about calculating the moles and calculating the mass, as well as stuff to do with Avogadro's number and calculating the number of molecules. So if you want to have a go, pause the video and the answers will be on the next slide. So the first question was all about calculating the moles of various substances. So the first one was 39 grams of aluminium hydroxide. So we're going to use our formula here of moles is equal to mass divided by the molecular mass, MR, M over MR. So the mass of this is 39 grams, so 39. And then MR, if we work it out for aluminium hydroxide, we need to add together our atomic masses. So we have to have the mass of aluminium being 27, then the 3 times the oxygen 16, the 3 times the hydrogen 1, comes out to be 78.0. Remember that we give our MR values to 1 decimal place. And so then by doing 39 divided by 78, we end up with our number of moles being 0.5. Secondly, we had to work out for 20 kilograms of copper nitrate. Now the key thing here is that it's 20 kilograms, not 20 grams. If we go back to looking at the units of our moles equation, the mass has to be in grams. So we have to convert the 20 kilograms into 20 grams by timesing by 1,000. And then we divide by the molecular mass, and if you work out the molecular mass of copper nitrate, it comes out to be 187.5. And so dividing those two together gives us 107 moles. And remember the unit for moles is MOL. Question 2 then wanted us to calculate the mass of various things. So to do this, we have to rearrange our equation. So we know that moles is equal to mass over MR, and so therefore mass is equal to moles times MR. Imagine timesing both sides of that equation by MR. The MR on the bottom cancels out, and we have moles times MR. So for the first question, with the 5 moles of chlorine, we're going to take the 5 moles, 5.00, and times it by the MR of chlorine. In this case, this is why it's important to give the formula of what we're dealing with. It was Cl2, not Cl. So we have 35.5 times 2, which is 71, and timesing them together gives us 355 grams. Then question B was 0.3 moles of the sodium carbonate with the 10 moles, with the 10 waters of crystallization. And so we have our moles, 0.3, and then we work out our MR of the sodium carbonate, and we include the 10 waters of crystallization. The MR comes out to be 286.0, and timesing them together gives a mass of 86 grams. Question 3 then wants us to calculate the number of molecules of chlorine, Cl2, in 6 moles of Cl2. Now remember, we said that 1 mole contains Avogadro's number of molecules of Cl2. Note that we're talking about Cl2, the molecule, so it's Avogadro's number of molecules. So if 1 mole contains 6.022 times 10 to the 23, 6 moles must contain 6 times Avogadro's number, 6 times 6.022 times 10 to the 23. And when we do that, we end up with 3.61 times 10 to the 24 molecules. Finally, question 4. We have a quantity of sodium contains 7.20 times 10 to the 23 atoms. What is the mass of this quantity? Now, the first thing to do here is to work out, well, what is the moles of sodium? We know that 1 mole contains 6.022 times 10 to the 23 atoms. Here we have 7.2 times 10 to the 23 atoms. So if we divide 7.2 by 10 to the 23, divide it by the 6.022 times 10 to the 23, and we end up with 1.2 moles. So that's how many moles of sodium we have in that number of atoms. Then we want to work out what the mass is. So again, we use that mass is moles times mR. And so the mass ends up coming out to be 27.5 grams. And a really useful way to the thing that I always remember for this is to remember that to get from mass to moles, we use the equation and we divide by mR, n equals m over mR. And if we want to go from moles to the number of entities, whether that be atoms or molecules or ions, we times by Avogadro's number. And then the reverse holds true as well. If I want to go from entities to moles, I divide by Avogadro's number. If I want to go from moles to mass, I times by the mR. Another thing to be really careful with in these maths questions is to note the consistency of the significant figures that you use. We can only ever give the answer to the lowest number of significant figures that we have in the question. So for example, if we take the very first question, 1a, we have 39.0 grams of our aluminium hydroxide. Remember that we give our mR values to 1 decimal place, so it's 78.0. Both of those are to 3 significant figures, so we give our answer to 3 significant figures. 0.500. Remember that if we have zeros before the decimal point, they don't count as significant figures. Zeros after the decimal point, or after a number, do count. So 0.500 is 3 significant figures. If it was 0.0500, that would still be 3 significant figures because any zeros that are before the first number, even if they're after the decimal point, don't count as significant figures. So thank you for watching this video. You can find more videos like this on my YouTube channel. If you found this video helpful, please leave a review on one of the tuition websites. I offer online tuition for chemistry, so please check my tuition pages for prices and how to contact me. And if you need any more help with your chemistry, feel free to drop me an email. I'll be happy to help.